Good morning, dear students. This is Asif Javed, course instructor, Real Analysis, GGM Science College, Jammu. In today's lecture, we will be discussing about Cauchy's second theorem on limits. Dear students, you must be aware about the Cauchy's first theorem on limits. I would like to make a quick recapitulation of what we have done in the Cauchy's first theorem on limits. In the Cauchy's first theorem on limits, we said that if we have a sequence of positive terms, and we said that if that sequence of positive terms converges to a limit L, then the sequence of arithmetic means also converges to the same limit. In Cauchy's second theorem on limits, if we have a sequence of positive terms and we suppose that the limit an plus 1 upon an exists, whether it is finite or infinite, then the limit of nth root of an as n goes to infinity, this is same as the limit of an plus 1 upon an. So Cauchy's second theorem on limits says that if one limit, that is an plus 1 upon an, it exists, then we get one limit free of cost. And what is that limit? That limit is limit an raised to power 1 by n. And moreover, it not only gives us the existence of this another type of limit, but it further goes on to say that the two limits become equal in this very case. The proof of Cauchy's second theorem on limits is very simple. Let me take the case number first. We have two cases. So the first case is if we have this limit equal to a finite number. Let me take that finite number as L. You are quite aware about the fact that if some sequence has a limit L, it essentially means that the sequence converges to L. So here in this very case, the sequence is an plus 1 upon an, so it will converge to L. So by the definition of convergence, for all epsilon greater than 0, however small, there exists a natural number m such that the condition gets satisfied. So you can see, if you can see the cursor, I am pointing the cursor here. So you can see that this an plus 1 upon an minus L, this is strictly less than very small quantity, and let me take that very small quantity as epsilon naught by 2, and this is true for all n greater than equal to m. Now as you know that an plus 1 upon n minus L, mod of this is less than epsilon by 2, this also means that an plus 1 by an, this lies between L minus epsilon by 2 and L plus epsilon by 2. Now what I am doing here, I am taking the value of n as m plus 1, m plus 2 up to n minus 1. Now why I am doing all this? Because this inequality, this gets satisfied for all the values which are greater than or equal to m. So if I start from m and I end at n minus 1, first of all I have to make sure that these are n minus m values. Now how are these n minus m values? See carefully. We have started from 1 and we have ended at n minus 1. But you have to keep one thing in your consideration, you have to keep one thing in your mind, that we have skipped m minus m values. So out of all the n minus 1 values, we have skipped m minus m values. So how many values we have actually taken? That is n minus 1 minus those m minus m values, and if you take that difference, then n minus 1 minus m minus 1, it comes out to be n minus m. So these are n minus m values. Now I am putting these values one by one in this expression. So if I first of all take m, and if I put m here in this inequality, then this turns out to be this. Now one by one I am going to put all these values in the above expression. If I take n equal to m plus 1, then this will turn out to be am plus 2 upon am plus 1, and this is again lying between L minus epsilon by 2 and L plus epsilon by 2. Similarly, I go on doing this, and finally when I put n equal to n minus 1 in the above expression, as you can see clearly here, then this turns out to be an minus 1 plus 1, which is nothing but an upon an minus 1, and that again lies between L minus epsilon by 2 and L plus epsilon by 2. Now what I am doing next, I will take the multiplication of all these expressions. Are you getting what I am saying? What I am essentially doing here, I am taking the multiplication of all these expressions. Now these are n minus m expressions. So when I will multiply all of them, then these L minus epsilon by 2, this quantity will get multiplied n minus m times, and similarly L plus epsilon by 2, this will also get multiplied n minus m times. Now what about these quantities which are there in the middle? If you see carefully, this am plus 1 and am plus 1 will get cancelled out, am plus 2 and am plus 2 will get cancelled out. Similarly, an minus 1 will get cancelled out by some an minus 1, which will be the previous one. So finally we are left with am and an. So that means if we take multiplication of all these entities, then we are going to end up with an upon am. So on taking multiplication of the middle quantities, we are getting this an upon am, and as I told you that these are n minus m times, so I can take raised to power n minus m, and similarly I can take raised to power n minus m. So the rest of the things are very straightforward. What I am doing next is I am multiplying the whole inequality by am. So when I will do that, I will get rid of this denominator am here, and am will get attached to these expressions. Now what next I am doing here, I am taking the nth root throughout, so I will get this expression. Now comes the important point here. If you see carefully these two terms, I am essentially talking about this, and I am talking also about this. So if I take n approaches to infinity, that is I am taking the limiting case, then you must be knowing the fact that if you have something greater than 0, and if you take the nth root of any positive real number, in the limiting case it turns out to be equal to 1. So if I take n approaches to infinity, this things comes out to be equal to 1. And here if you take n approaches to infinity, m by n goes to 0. So all in all this goes to L minus epsilon by 2. Similarly this will go to L plus epsilon by 2. That means this whole turns out to be another sequence which goes to L minus epsilon by 2, and this goes to L plus epsilon by 2. Now again using the basic definition of convergence, that if something goes to L minus epsilon by 2, then that sequence minus L minus epsilon by 2 is less than very small quantity, and that very small quantity I am taking as epsilon by 2, and this is true for all n greater than equal to m. Similarly, the other sequence goes to L plus epsilon by 2, so again this mod of this minus this goes to less than epsilon by 2, and this is true for all n greater than equal to m2. Because the stages may vary, one sequence may be behaving differently than others, the rate of convergence may not be same, so I am taking stage for one sequence as m1 and the stage for another sequence as m2. Now having done all this, now I am again coming to the basic what we had done in the convergence, that if this minus this is less than epsilon by 2, then this essentially means that this quantity, this lies between L minus epsilon by 2 minus epsilon by 2 and L minus epsilon by 2 plus epsilon by 2. And this turns out to be, this boils down to am raised to power 1 by n, L minus epsilon by 2 raised to power 1 minus m by n. This lies between L minus epsilon and L. And this is true for all n greater than equal to m. Similarly, if you go on doing the similar sort of exercise, here is a mistake. If you have pointed here, this is not minus here, this is plus, so please rectify it. So this is am raised to power 1 by n, L plus epsilon by 2 raised to power 1 minus m by n. This comes out to be greater than this and less than this, and this turns out to be that this sequence, that is L plus, again I am repeating, this is L plus epsilon by 2. This comes out to be lying between L and L plus epsilon, and this is true for all n greater than equal to m2. Now I have three expressions. This is my equation number 3. If I go back, this is my equation number 2, and further I have equation number 1st. If you see carefully equation number 1st, then this an raised to power 1 by n, this is less than this quantity. But if you read this quantity in view of equation number 3, then in view of equation number 3, this comes out to be less than epsilon. L plus epsilon. That means an raised to power 1 by n is indirectly less than L plus epsilon. And what about this quantity? If you see this quantity in view of equation number 2, then it is strictly greater than L minus epsilon. So indirectly I can say that this an raised to power 1 by n, this is indirectly strictly greater than L minus epsilon. So all in all, what I can say in view of all these equations, what I can say is that this an raised to power 1 by n, this lies between L minus epsilon and L plus epsilon. Now one thing which we have to settle is there are different stages. In the first equation we have stage m, in the second we have m2, m1, and in the third we have m2. So to settle all this, we will take p as the maximum of m1, m2 and m, so it will take care of all the three stages. So that's what I am exactly doing here. So n raised to power 1 by n, this lies between L minus epsilon and L plus epsilon, and this is true for all n greater than or equal to p, because p will take care of all the three stages. And this essentially means that an raised to power 1 by n minus L, the mod of this difference is going to be less than epsilon for all n greater than or equal to p. By applying the basic definition of convergence, this means that this limit is equal to L, but L is nothing but this is limit n approaches to infinity n plus 1 upon n. So the proof is over. So this is all I have in this lecture. In the next lecture, I will tell you about the infinite case, and that infinite case is, you can say, just the offshoot of this case number first. Thank you so much for joining me.